We're going to look at a few circuits where it's not easy to simply combine your resistors in series versus parallel, but these little rules we've been looking at, the conservation of energy and conservation of charge rules, still apply. They're technically called Kirchhoff's rules. The conservation of energy rule is also called the loop rule. It means if you go around any loop, starting in one spot, coming around until you get back to that same spot, if you sum up all of the voltage drops and gains throughout the loop, they have to add up to be zero. Because if you start and end in the exact same spot, well, there's one voltage there, so there's not going to be any difference overall between that point and itself. So the loop rule is our conservation of energy, which we've looked at already. We're going to apply it to another circuit, though. The other rule, the conservation of charge, is called the Junction Rule. Basically, it tells us whatever current's flowing into the junction has to continue outwards and flowing out. So if you sum up all of the current flowing in, it has to equal the sum of all the current going out. So for example, over here we have a circuit with 3 batteries. Now, I'm not claiming that you need 3 batteries set up in this in some practical way. This is to practice with the rules. We need to understand these rules in order to look at circuits with resistors and capacitors as well. So, just need a little practice. So as we approach a problem like this, where we have multiple batteries, multiple resistors, it's not easy to say what resistors are in parallel versus series. Some of them are. For example, on this branch, these 2 resistors need to be in series because you have to pass through both of them if you're moving along this branch. So the approach, what you want to do is, number 1, you want to draw in your currents. You want to draw in the currents that are flowing. If you have 3 branches, then you need 3 currents. Okay? If you're not sure what direction they will be in, then just make it up. Draw in a direction and just use it for solving the problem. For example, on this right-hand branch, generally by convention, current flows from high to low. So we would expect current to flow in this direction along this branch. I'm going to call that I1. So the current from this junction all the way on the right back to this junction, we're calling I1. In the middle, from this junction up through the middle to the top, we'll call I2. And then on the the left-hand side over here, we need an I3. And if we follow the convention, current flowing high to low, we can write current flowing this way. Now, not all of the currents are actually going to go in the direction I've indicated. They can't all flow into this junction into a never-ending pit where the current disappears. But it doesn't matter. Once you've chosen your directions, you're going to write your equations. These 2 rules are going to give us some equations to use. You're going to write your equations according to the way you've drawn your picture. Keep in mind, current, remember current by definition flows from high potential to low. Since I've drawn the current flowing to the left through this resistor, that means I'm defining the right side of this resistor as a higher potential and the left side of the resistor a lower potential. For this one, the left side's higher, the right side's lower. That's going to be important when we do our loop rule. So here, the bottom part's higher, the top part's lower. Here, bottom's higher, top's lower, right's higher, left is lower. And that's just because of the direction we've drawn our currents. All right, we have 3 unknowns in our equation. That means we need, in our system, we need 3 equations to work with. One of the equations always needs to be the junction rule. Okay? So the junction rule, pick a junction. Doesn't matter which one. It can be this one or that one. If we're looking at this junction, we want to add up all the currents that we've drawn that would be flowing towards that junction and set them equal to the sum of all the currents that are flowing away from that junction. From the way we've drawn it, no currents are flowing towards this junction, so the current in is 0. That has to equal the sum of all the currents flowing away. Well, the currents flowing away are all of them, so I1 plus I2 plus I3. Okay with that? Junction rule is not too hard. Loop rule. Loop rule is conservation of energy. You have to do a loop. There's 3 possible loops in this circuit. There's the left-hand loop, the right-hand loop, and the whole entire circuit loop. You only need 2 of them, because we already have 1 equation. We only need 3 equations, so we only need 2 more. It doesn't really matter which 2 you do. Let's look at the right-hand side. The rule for the loop rule is that you start and end in the same place. Where you start is not important. What's important is that you end up where you started. So let's start right here, bottom right-hand corner. It doesn't really matter which direction you go, whether we go clockwise or counterclockwise. It doesn't matter. If we go counterclockwise, as we go up, we're going to see a voltage drop. Since we're passing this through this resistor, going from high to low, we're going to see a drop. We need to know the voltage drop. The loop rule is adding voltages, not resistors. It's not adding current, it's adding voltages. What determines the voltage drop across this resistor? Current. The current flowing through it, and?
The resistance.
Its resistance. So it's a drop because we're going positive to negative. The voltage will be I1 times that resistance, which is 10 ohms. So that's the voltage drop. As we keep going, we're going to come to this battery. We're passing the battery from the low end to the high end. So we're going to see a gain. We're going to see a gain. That already is voltage, so we see a gain of 40 volts. We keep going, we're passing through this resistor, and again, because we're going positive to negative, we're going to see a drop. Current times resistance is the voltage, so I1 times 10 ohms is the voltage drop across that resistor. Now we need to decide, should we come back down through the middle, or do you want to go and complete the entire outside loop? Middle? Okay. So as we get to this junction, we're going to come down through the middle. Gain or drop?
Gain.
A gain, because we're going negative to positive. So we're going to see a gain, so plus, its voltage is going to be I2 times its resistance, 20 ohms. I'm going to have to erase our rules. Next thing we come to is this battery. We're going to see a gain or a drop? Drop of 40 volts because we're going from the positive to the negative plate. Keep going. We don't pass by anything else. We get back to where we started. So all of this stuff has to equal 0. If you add up all of the voltages, they will add up to be 0. So what we find out here, we can combine these terms. We get negative 20 I1. This 40 and that 40 cancel, so plus 20 I2 is equal to 0. So basically, this one tells us that I1 is equal to I2. They're the same. Okay, we need one more loop. We have 2 equations now, but we have 3 unknowns. One more loop. We can either do the whole entire loop, or we can do the left-hand side. Doesn't really matter. But left-hand side. Okay, let's start right here at the bottom of the middle branch, go up and around on the left-hand side. So as we go up, we're going to see a gain of 40 volts. As we move through that 20 ohm resistor, we're going high to low, so we're going to see a drop of its voltage is I2 times 20 ohms. Turning left, we're going through that top 10 ohm resistor on the left. We're going negative to positive, so we're going to see a gain. The voltage through that one will be I3 times 10 ohms. We're coming down through the battery. As we go down through the battery, we're going positive to negative, so we're going to see a drop of 20 volts. Keep coming down, come down that middle, this last branch right here. Come through this resistor, we're going to see a gain. The voltage drop across that resistor is its current, which is I3, times its resistance, which is 10 ohms. That gets us back to where we started, so that has to equal 0. So let's simplify this down. The 40 minus 20 is going to be 20 volts. Let's see, we only have the 1 I2, so 20 I2. And then we have 2 I3, so plus 20 I3 is equal to 0. So now we just need a little algebra. Algebra is not too hard though. We know I1 is equal to I2. So up here we could say instead of I1, we could put I2. So that means 0 is equal to 2I2 plus I3. Or I3 isn't equal to negative 2I2. I2 and I3, in place of I3, let's put in negative 2I2. So 20 minus 20I2 plus 20 times I3 is negative 2I2. So 20 minus 20I2 minus 40I2 equal to 0. So 20 is equal, take that to the other side, 60I2. So I2 is 20 over 60, which is 1/3. So we have 0.33 amps flowing through that middle branch.
Since I1 is equal to I2.
Exactly. I1 is also 1/3 of an amp. And I2, I1, we know I3 is negative 2I2. So I3 is negative 2/3 of an amp. That negative sign is significant. Getting a negative sign means current I3 is actually flowing in the opposite direction than what I've drawn. So I3 is really going this way. Basically, these two 40-volt batteries are overpowering the 20-volt battery and forcing current to flow the opposite direction.
We also use matrix.
Yes, you can use matrices if the currents are the only unknowns. You can't use matrices if anything else is the unknown.
Well,
So-
if you have enough equations, you can have.
But the problem
6
is, we're never going to do anything more than 3 loops. And the 3 loop equations are not linearly independent. Any 2 of them always gives you the 3rd. So you have to use the junction and 2 of the loop rules. If you don't know your currents, then yes, matrices works great. If you know one of your currents and don't know something else, the matrices aren't any easier than anything else. Questions? So half the battle is just getting the equations. If I give you a problem like this on the test, I look at your equations. I don't spend a whole lot of time going through your algebra. Okay? I make sure your starting point is good.